Stacking fails quietly when base models predict rows they already trained on. Out-of-fold predictions give you clean meta features instead. This is the workflow you'll know how to run when we're done, which builds leakage-safe out-of-fold stacking features for held-out rows. I'm Professor Pi, teaching AI foundations with simple Python. When you stack models, the second-level model needs honest signals. Base learners must never see the rows they're later asked to predict. If they do, validation looks great, but the stack collapses in production. Out-of-fold predictions fix that by making each row look like a held-out example during base training. Practically, that moves a model from overconfident and fragile to reliably better on new data. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, let's visualize the folds on a tiny dataset, so nothing mysterious hides in the splits. This snippet shows how KFold from scikit-learn slices our tiny dataset into leakage-safe folds. We fix 8 easy-to-see feature rows and matching labels. Then use KFold with 4 splits, so each index becomes a held-out example exactly once. Converting the splitter generator into a list gives a simple audit trail of trained test index boundaries before any estimator touches the data. Finally, summarizing fold sizes and the sorted counts of positives helps us spot any class mix issues we'll want to watch later. Now that we can see the folds, let's create a baseline to prove out-of-fold probabilities are leakage-free and easy to interpret. This example demonstrates cross-val predict, turning DummyClassifier priors into per-sample leakage-safe probabilities. The DummyClassifier never trains on held-out rows, so strategy equal prior returns probabilities that mirror the class mix seen only in the training partitions. Reusing the same splitter keeps the folds identical to our visual check. And method is predict proba gives a 2-column array from which pos prior pulls the positive class column. Rounding and listing the unique probability levels makes it obvious how each fold's class ratio affects the held-out scores. And the mean probability matching the training prevalence confirms these out-of-fold features reflect real distributional signals without cheating. Baseline in hand, we should compare a couple of real learners so we can pick good base models for the stack. This code ranks our base learners using cross-val predict-driven accuracy comparisons. By keeping the training data identical across estimators, reusing the same splitter and baseline setup. Differences in accuracy come from model behavior, not split noise. Inside the loop, cross-val predict clones each estimator per fold and accumulates out-of-fold predictions, which we compare directly to Y to compute accuracy. Sorting those results surfaces the best candidate and the margin to the runner-up. Seeing the decision tree win by a clear gap tells us which learner should contribute stronger signals to the stack. Next, we turn per row out-of-fold probabilities into features, so the meta model has something informative to learn from. This snippet assembles leakage-safe stacking features by combining original inputs with out-of-fold probabilities. The tree of proba array is produced with the same splitter, so the DecisionTreeClassifier never sees the 2 rows it later predicts for. Slicing the positive column distills a single interpretable meta feature that captures how confident the tree is for each observation. np.columnStack then glues the raw X columns with pos prior from our DummyClassifier, so the meta matrix contains both simple prior signals and the sharper tree predictions. Computing meta means offers a quick sanity check that these engineered features sit in sensible ranges before we hand them to the meta learner. Finally, we'll train and evaluate the meta-level model while keeping the stacked training set fully leakage-free. This example trains the meta-level logistic regression on the stacked feature set to close the loop. Because StackX holds only out-of-fold base predictions, cross-val predict can safely evaluate the meta-estimator without hidden leakage from shared rows. The meta-classifier is lightweight solver equals liblinear, suits this tiny dataset, and random state keeps results reproducible. After collecting stack-pred, we compute accuracy and an explicit error count, which also serves as a quick regression test if you scale the workflow. Hitting perfect accuracy here shows the stacking pipeline preserved validation integrity, while capturing stronger signals than the naive prior baseline. If you map this toy example to a real project, swap the tiny dataset for your full training table, and the simple tree for a more expressive base model. The same folding and out-of-fold recording pattern scales. Keep an eye on class balance per fold and measure runtime when you bump up data size. Recap. Out-of-fold predictions are per-row estimates produced by models that never saw those rows during training. Use them when you want to stack models or build meta features without leakage. Caveat: poor fold design or extreme class imbalance will still bias your meta features, so check per-fold distributions. Next step: try increasing the number of folds and measure both accuracy and runtime to find the best trade-off for your dataset and compute budget. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.